In this lecture, we're going to look at how power functions are represented graphically. So we're going to recognize the shape and boundaries of a power function when it is shown graphically. We're going to distinguish between a rational power, such as a square root, and an integer power, such as a square. We want to recognize when an equation is in a power model, and we want to determine the physical meaning and units of parameters of a power function. So power laws have the form of y equals b to b times x to the m. If m equals 1, you have a linear function. If m equals 0, you have a constant function. So a linear function is just a special form of a power model. If you have a square root, it curves up. If you have a square root, you have a concave type parabola forming where a squared or another power is going to give you your traditional power model shape. So an example of power relationships, you have V is equal to, some examples of a power relationship, you have your volume of is a lot of your geometric formulas. So for example, volume is 4/3 pi r cubed. You have your kinetic energy, where kinetic energy is 1/2 your mass times your velocity squared. You have inverse relationships are also power laws, such as your ideal gas law relationship between volume and pressure. So that would be a power relationship when the power would be -1. So for power laws, if you have a negative slope, you have shapes that go downwards. For example, you had y is equal 1/x on this side. Make sure that you remember that y equals x to the -1 is not the same as y is equal to -x. Sorry, this y is 1/x. This y is -x. They are not the same. So what are the units of the constant 2 in this case? So the equation that we're comparing it to is Ke is equal to 1/2 mv squared. So if we compare the two, our exponents are always unitless. So exponents are always unitless. So the 2 in this case is unitless. If we're trying to find the units of the constant 3.73, we'll compare our two equations. We need kinetic energy on the one side, which is in joules. So if we solve the equation for 3.73, we'd have kinetic energy per velocity squared. So we would have joules per meter squared per second squared, which is a kilogram meter squared per second squared, times a second squared meter squared. If you keep canceling out your units, you're going to get kilograms, which by comparison should make sense since the m in our equation is since the 1/2 m is what we'll be comparing, which m has units of kilograms. So it's the physical meaning of the constant. So if we compare our two equations again, we have 1/2 of m is equal to 3.73. So 1/2 of our mass is equal to 3.73. So we want to find the mass of the object. So we have 1/2 of our mass is equal to 3.73. So we have our mass is approximately 7.46 kilograms or 7.5 kilograms. So what are the units of the constant -2 in this case? Again, -2 is an exponent, so they are unitless. All exponents are unitless. What are the units of the 1205? So 1205 would be h times r squared, which is centimeters times centimeter squared. So 1250 has units of centimeters cubed. So let's compare these two relationships. So our theoretical equation was based on volume, which we were actually representing in terms of height. So if we compare our height and version of our volume equation, so here we have our heights, we have our volume divided by pi, and we have our r to the -2. So the physical meaning of our constant is actually our volume divided by pi. So what is the volume of the container we are designing? So we have our 1205, which is volume divided by pi, which means our volume is approximately 3,785.6 centimeters cubed, which is approximately 1 gallon. If we had a container of radius 2 centimeters, how high would the container be in units of feet? So we have our h is equal to 1205 divided by 2 centimeters squared, which h would then be 301 centimeters, or approximately 10 feet. If I had a container of radius 10 centimeters, how high would it be in terms of feet? It's just did that. In this example, we're going to look at what are the units of the constant -1. Again, it is an exponent, so its units are, it is dimensionless, it does not have units. What are the units of the constant 98? Well, if we compare our equations, we have 98 is equal to our inductance times our length, which is milliamps times henries. As a reminder, a henry is a volt second per amp. So we have amps divided by 1,000 because we were looking at milliamps times volt seconds divided by amps. So we have volt seconds divided by 100. So we have volt milliseconds. What is the current measured after 75 milliseconds, and what is the value of the volt charging voltage? So we have 98 volt milliseconds is equal to voltage times time. So our voltage is equal to 98 volt milliseconds divided by 75 milliseconds. So our initial charging voltage is 1.3 volts. So this is an example of how to look at some power relationships and how to gain information from a graphical plot of a system that we were looking at.